Hi, I'm James Nichols, and in this tutorial I'm going to show you how to create your own small piece of the universe using 3ds Max, thinking particles, and then rendering in Krakatoa. So to begin this tutorial, I would like to create a bounding box just as a point of reference for where our particles should be generated, and for this simulation I'll be using the dimensions of 1000 by 1000 by 1000, and my system is set to meters, but this can be units or whatever your system is accustomed to. And for now we can set this to wireframe because we don't actually want the box to be rendered, and for that reason we can set this box to be non-renderable. So now that's fine, we can leave this in the scene and we don't have to worry about the box being rendered. And then if we could create our thinking particle system, and what we would like to do is begin generating particles within the volume of the box. So we can start by creating a group. We'll name this group stars, and this is the only group we will need for this simulation. And our first dynamic set, name this generate stars, and we're going to generate our particles using a operator generator position born operator linked to a volume position helper using our position node, and with a node helper which will be linked to the box. So from here our simulation will begin generating particles within the volume of the cube. But for our simulation we would like a set number of particles or stars. So for this simulation I found that 1000 works well with the dimensions of the cube. And if we just update our scene, now you can see we have 1000 particles within our cube. But due to the scale of the scene, if you can see this properly, the cube is hollow with the particles sticking to the faces of the cube, and this is simply because of the volume position node, and the thickness spinner is set to 100, whereas our scene is too large and 100 isn't enough. So if we just ramp this up to quite a high number, I think a good 9,000-10,000 is good, and as you can see now the particles are starting to fill the box. And if we just put this to an absurdly huge number, there we are, the particles seem to be in a very random spread within the cube. Okay, that is the first step of generating the particles for the simulation. We also want our particles to live for quite a while throughout the simulation. Again, 1000 seems to be best, and we want to eliminate any speed or direction that they have at the moment. So just setting these values to 0 is fine. If we update our timeline to match our lifespan of the particles, and now the particles are alive throughout the entire animation. Okay, so now if we collapse this generation dynamic, and if we create a new dynamic, and this dynamic will be giving us our forces, so I'm going to call this force. It's best not to stick to generic names when naming dynamics in case of loading or saving dynamics out as black boxes. It just helps to avoid confusion. So for this simulation we will not be providing our particles with their own form of gravity, unlike the real universe where gravity is applied. For this simulation, we will be faking the gravity simply by using a search radius for each particle. And to do this, we will be using the p-pass AB. Okay, and what this does is it relates each particle from one group to a corresponding particle within another group. And this is good because we would like all of our particles to search for each other. So for this simulation, we will be using the p-pass AB, where the groups are both stars. Might I add that I have probably forgotten to set our generated particles to be moved to our stars group. So now all of the particles being born using this position born operator are sent into the stars group and are called in the p-pass AB. As I said, we won't be using gravity or for this simulation. We'll be using a search distance, and for this simulation I believe a search distance of 5,000 is an appropriate number. Bear with me. And the actual number, this is 5,000. That's perfect. So now if you scrub through the timeline, you'll get absolutely nothing. That's because although the particles are searching for each other, they have nothing to do. And what I'm going to tell the simulation now is that once you've found the corresponding particles within the search radius, I want you to apply a force and have a force applied at the same time. So all of the particles from the stars group, particle A, are included in the force. They are being affected by the force, but then the position of the force is being provided by the group B, which is in fact the same group. So each particle is being affected and is being the position of the force. Okay, so that's the one of the principal set stages for the simulation. And if we give them all a spherical force, then they will seem to be providing a form of gravity. And so now if we scrub through the timeline, we get very slight movement, and this is because forces from the force operator are very low indeed. And if I just grab these numbers, so minus 10 and 100. Okay, for this simulation, for this size, we give a strength value of minus 10, which is an extraordinarily high value, but in this circumstance it seems to be appropriate. And one major value to make sure the system runs accordingly is the force variation. Now the force variation will give the impression that some stars are applying more force in a sense, and in that way you could say that these stars have more mass and therefore more gravity. So they don't actually, they're not set up to have a gravity of their own, but with the variation it gives the effect, the illusion that some particles are more weighted than other. So 100% variation will create stronger forces of gravity within the particle field. And if we run this simulation now, might I add that when using a large amount of particles, it's a very good idea to disable real-time playback, just so that the particle system can update along with Max and its timeline. If we play this now, you can see we are already having the basis of our simulation started. But the most obvious point I can show you now is that the particles are breaking free of the gravitational force, and a lot of particles are just floating away. Another important stage of the simulation is adding a form of friction. Now, although in space there's no real friction, for this simulation friction is needed, simply because some of the forces are so strong and they are so close together that they overshoot their pull and are flung completely out of the simulation entirely. So if we just add just a standard force, a friction dynamic operator, and add that into the particles, and if I just grab the appropriate value, 0.1, a very small frictional force, but it is just needed to glue the universe in place. And now if we run through the simulation again, we have our galaxy clusters forming, and we've got the odd particle here breaking free, some particles just not being affected by the forces at all, and there we have it, a very, very small scale version of the universe simulated on a home computer.